Okay, so I think that we have already gone on over what are the most important aspects of Chapter 9 already, honestly. But there's just a couple more things to mention, and actually, we're going to skip a large section of it. So, one of those things is this idea that, oops, let me skip down in the slides here. The pressing against Earth is the sensation we interpret as weight. So, in other words, the support force we feel against gravity is interpreted by our brains as weight. So, free falling, well, I'm skipping ahead of myself. So, you have weight against an object due to the gravitational force pushing on you or attracting you to the object, and the support force against you is what makes you feel like you have weight. Though having no support force feels like there's no gravity on you, the feeling of weightlessness does not actually mean there is no gravity acting on you. So, for example, here we can see that there's the weight of the person, and when they're falling at the same rate as like the things around them are falling, it seems like they are weightless, that they are free falling, but they still actually have gravity acting on them. Same in these examples here. There's the same sensation of weightlessness in both of these examples, but there actually is the force of gravity acting on the people. And so, like, space stations, you might think, oh, they feel weightless because there's no gravity acting on them. No, the space station is actually still really, really close to the Earth relatively. Um, it's not that far from the Earth, okay? It's that it's rotating or going around the Earth and is continually falling, so everything in it is in continual free fall. And so this can be mimicked in planes where they essentially have the plane for a very short amount of time. Excuse me, I have a terrible cough. The plane for a very short amount of time fall downwards at the same rate as you're falling, and so it seems like everything's falling in the same rate so that you're in free fall. That's the same thing happening in the space station. The the space station is only 408 kilometers away from Earth. For perspective, the moon is 384,000. Okay, so it's really not that far away. It's quite close. The gravitational difference is not that much. That does not account for why you someone would feel weightless in the space station. No, it's because they're continuously falling around Earth, and the things around them are also falling around. So that gives them the feeling of weightlessness. Like the water bucket, remember the water is falling in the bucket continuously, but is falling at, like, as it's falling around, it's still kept in the bucket, or the girl in the free falling escalator. There's a gravitational force on the astronauts, but the space station and them are maintaining orbit due to inertia. There is no support force because the astronaut and the space station are both under the same gravitational force, continuously falling towards the Earth while maintaining orbit. So I'd like you to pause once you get to this point. I want you to pause this video and watch this one using the links in your notes and answer the video questions and talk about the answers with the people next to you. Maybe the sub, once you watch the video, the sub can have you answer the video questions. You can talk with the people next to you, and then the sub can call on a couple different people, or some groups can share their answer to the video question. And then the same thing for this one. Why are astronauts weightless? I want you to then watch this one and then talk about it with the people next to you, answer the video questions, and then have a couple people share your answers. Okay? So hopefully you've paused this video, you've stopped this video, and you've been able to do that. Now, all this on tides we are going to skip. I don't want to cover it. So whoops. We're going to skip all of that on tides and go all the way down to gravitational fields. Any of the questions in the notes that regard tides, So any of the practice questions, if they're about tides, they're not going to be on the quiz. So there you go. Okay, gravitational fields. Now, I remember someone asked, how does gravity work? And I said, if you definitively knew how gravity worked completely, you should not be in this class, right? You should go and talk to some of the smartest people in the world and explain it to them. Because there's developing theories, and it has to do with gravitational fields, but gravity's not fully understood. At least that's my understanding. So, gravitational fields are the region of space surrounding a body in which another body experiences a force of gravitational attraction. So, an object has a gravitational field, and other objects have attraction to it. And so this represents the gravitational field lines of Earth, and where the field lines are closer together, the gravitational force is stronger, and as the field lines become more separated, as they move further and out from the object in which they originate, the force of gravity becomes weaker. I'd like you to pause this video. I'd maybe read it out, but with my cold, I'd rather you pause this video and take a second to read what's here. Okay, so hopefully you've paused this video and had a second to read what's here. And again, this kind of gives you some ideas on some like explanations of perhaps how gravity works. And you can look up things like if you look up LIGO, LIGO on Wikipedia, you'll find that there's this huge center, or there's these huge places where they are trying to detect gravity and figure things out about gravity and how gravity works. It's interesting. If you're really interested in that, you could look up LIGO Veritasium. And if you look up LIGO Veritasium, there's a video called The Absurdity of Detecting Gravitational Waves. And so then, yeah, you can learn more about it. But my understanding is that it's still not completely known really how gravity works, and it's open development. So remember, the force of gravity depends on the distance from the center of mass of the object. So not the surface of the object, but the center of mass, right? So if you get on a skyscraper, your weight is not appreciably different than it is on the surface of the Earth, because we're not measuring the distance to the surface of the Earth, we're measuring the distance to the center of the Earth. And so the difference to the center of the Earth from the floor to the top of the skyscraper is not that different, relatively, in terms of percent. So being closer to a really dense object, which takes up less space than a less dense object, is increasing the distance from the center of mass. So if you recall, we watched that video of the guy showing how there's gravity by using the lead blocks, and he said that you use lead blocks and not a car, because even though the car might have more mass than the lead block, the car takes up a lot more space, and you need something that's really dense and doesn't take up as much space, so the gravitational force of attraction is stronger, because then there's less distance between the objects. So just to demonstrate this, if we have these two examples, let's say planet A and planet B have the same mass, but a person on the surface of planet B would have much more force of gravity than on the surface of planet A, because they're actually much closer to the center of the gravitational force. Some other random things to mention, kind of from this chapter: black holes. Black holes are just huge objects of mass, and so they take everything in and swallow it, and basically it loses all its properties because there's so much gravitational force. Why is the Earth round? Because the gravity of the center of the Earth pulls everything in to round it out. So it's essentially round. And the same general logic explains how solar systems get their round elliptical shape. And this idea is something I cover in physical science, and it's called accretion, where things start as a ball If you want to learn more, you can look up accretion. Things start as a ball, and then um, the dust or particles collect into larger balls, which become planets because of the gravitational force of attraction. And then, due to conservation of angular momentum and how accretion works, which we're not going to get into too much right here, but that ball eventually spreads out into more of a disc-like elliptical shape. And so that process is called accretion. And so those attractions of gravity also explain how the elliptical orbits of planets and solar systems form as well. So that is it for chapter 9. So after you had done this and watched those videos and answered those questions, you should take the remaining time to work on chapter 9 practice problems. And I'll ask the sub how much time you had to work on those, how far you got, etc. Perhaps quiz next class or the quiz after that on chapter 9. Very good.